So maybe I'll just see what I can do with this.
Yeah, Vishwa, we are streaming now.
You can see?
Yes.
Okay.
Okay, we'll start.
Yeah, I think we can get started, Bhadraj.
Okay, great, cool. Okay, thank you, Nandan and Vishwa, for this opportunity. And good evening and welcome everyone to this lecture on the black holes. So in this lecture, we'll be looking at some of the basics of black holes, their types and structures, what they're made up of, and highlight some of the discoveries that are related to the black holes in the recent times. And we would also look at some of the discoveries that happened in the last few years, which were very dramatic and mysterious as well as the black holes themselves. And then we will look at a couple of videos that we will take a journey towards the black hole from the Earth and see how it goes. And then we'll end with question and answers. Okay, so let's begin.
Yeah,
So I can move forward, right?
Yes, go ahead, please.
Okay, cool. Thanks. Okay, so let's look at what is a black hole. So basically, it's one of the mysterious place in this universe. So I said place, not an object. We'll see why shortly. Okay. So by definition, it's a place where gravity is so strong that nothing, not even light, can escape. What it means is, if you throw a light on this, you will not be able to see that the light will come back. And the black holes themselves do not produce any light on their own, so they appear black, and hence they're called black holes. This is a place where we see that the gravity is very strong. Anything that comes near to it will get sucked into it and will not come out at all. So that's the strong gravity place that we have in the universe, and again, mysterious again. So before we see how the structure and what the black hole is about, and let's look at gravity. Let's use it what we understand by gravity. I know we know it, we experience it all the time, but that gravity is another mysterious thing, as mysterious as the black hole itself. Okay, so gravity is not a force or a field. This is what we studied in our school times, probably, that gravity is a force. We can define it by using a Newtonian formula, but gravity is due to the curvature of space-time. Einstein said that both space and time are not different entities, but they are one and the same. They're just space-time. So as we move in the space, so we move in the time, and vice versa. As we move in the time, we move in the space. For example, if now we are like all sitting idle in front of a computer or a mobile, but the time is passing. If you remember, the Earth is moving, Sun is moving, solar system is moving, and the entire Milky Way is moving. So we are never at rest anytime, hence the time moving. So that's why it makes sense to say it is space-time as a single entity. So in the space-time, what happens is, if we place an object, for this explanation, we can consider space-time as two-dimensional, although it is three-dimensional as we can experience. But if you consider it as two-dimensional, and if we place a heavy object somewhere in the space-time, the entire space-time bends or curves itself, creating a web. And due to this, any object that comes close to it will start falling, start moving towards it. And that's gravity. That's how gravity works. So gravity is stronger when we are close to a heaviest object, and it is not that stronger when we are in the lighter object. So imagine if you place more heavier objects, like what white dwarf stars or a neutron star. Neutron star is a very star which is very tiny but has a lot of mass due to its large density. What happens is we see a space-time getting distorted. We see that it's bent so much that the space-time will stop behaving as a space-time. The relation between the space and the time. As we move in the space, we move in the time. So that gets disturbed. And again, this is due to strong gravity. Now, let's look at the black hole on the right-hand side. What happens to the black hole? Black hole, the space-time is completely curved inside, creating an infinite depth well, where any object that falls through it, which will never come out, which just falls through it, we will never know what will happen to that object. So that's why the gravity is so strong around the black hole. So within the black hole, the space-time is completely bent, distorting the space-time structure itself. And we have some areas within the black hole itself called as the event horizon, which is an imaginary line in which any object that falls through it or just crosses it, it will never come out, not even light. We could see the light up to the event horizon, but not beyond that. We don't know what happens beyond that event horizon. And any object that falls through it, just disappears forever into the black hole. We'll never know what happened to that. And there is singularity. There's a point within the black hole, at the center of the black hole, where all known physical laws, as we know them, break down. They do not apply anymore. They do not operate because at this time, at this moment of place within the black hole, singularity, where the time itself stops. Time doesn't fly anymore. It just stops. So it's very mysterious. And as a black hole, they are mysterious things themselves. Okay. Now, let's look at how these mysterious things or mysterious places form in the universe. Black holes are basically part of the stellar evolution. How the stars born, how the stars die. They just behave like humans. They're born, they live for some time, and they die. It depends on how big the star is, how much mass that star contains. It decides the fate of that star. Okay, so all the stars start from a protoplanet or the nebula, which is again a remnant of other parent star. It goes and forms a lump of the matter. It starts producing its own energy and the light. And eventually, when it nears to the end of its life, depending on how much mass it has, either it turns out to be a white dwarf at the end, where the mass of that particular star is less than 1.4 mass of the sun, which is called as the Chandrasekhar limit, formulated by Chandrasekhar. And if the mass of that star, which is dying, is between 1.4 and 2.5 mass of the sun, then it becomes a neutron star. Heavy dense star, large mass with large density, and occupying a very small space. But if If a particular type of supernova occurs and the mass of the star is more than 2.5 or 3 times mass of the sun, that star will eventually end up as a black hole. So this is how the black holes form as we know it. We have recently discovered there are other ways of creating black holes as well, but we'll come to that. So this is how the black holes came into existence, and there are various types of black holes. And the one which formed due to this stellar evolution is actually called as a stellar black hole because it is formed out of a star. Typically, it is 10 to 20 solar masses. When I say solar masses, is again compared to the mass of the sun. And there are intermediate black holes. It's another type where there are a little more bigger ones, like 1,000 solar masses. And there are still more bigger, the supermassive black holes, which are millions of solar masses. So these are the supermassive black holes are usually found at the center of galaxies. And you'll be surprised to see that in how these black holes come in various sizes. Because black holes do collide with each other due to gravity, and then they form a bigger black hole. And that black hole gets absorbed by another bigger black hole. That's how the size gets increasing, and that's how they become, bigger in the size. Scientists also have predicted that there is another type of a black hole apart from these, which are called as primordial black holes. They predicted that these kind of black holes might have formed right after the Big Bang, just 1 second after the Big Bang. And the sizes of those primordial black holes range from anywhere to smallest possible size in the universe, which is the Planck constant, Planck scale, to the planetary star or to the supermassive black holes. So its range is wide. So this is just predicted. There is no observational evidence so far for this primordial black hole. But again, we will touch upon this primordial black hole in a while. So hold on to that. Now let's look at what the black hole consists of, what it is made up of. This is a typical structure of a black hole. So as such, black holes are black. We cannot see them in the space because space itself is black. So if there is a black hole, again, that will be black. We'll not be able to see them. But just in case a star wanders around and gets very close to the black hole, what happens is, due to strong gravity of the black hole, star starts ripping apart, just breaking apart. And some of the material of the star starts falling into the black hole. And some of the other material, due to heavy gravity again, starts rotating around the black hole. And because of the friction, it starts glowing. And that's the thing that we can see. We cannot see the black hole directly, but we can see what's circling around it. And this is one of the structure. There's a black hole here, and there's a star here, which is all the material is falling apart. If we zoom it, we can see there's a black hole in the center, and there is a material revolving around that black hole due to gravity. And it's glowing because of the friction and this strong attraction of the gravity. So this revolving material is called as accretion disk, which is a superheated gas and dust. This entire material is coming from that star, which is falling into the black hole. And right next to that black hole is called as photon sphere, which is a hot plasma. Again, which is a superheated material, which is glowing very bright due to the large friction and large speed, which is circulating around the black hole. And we also see that perpendicular to this accretion disk, there are jets coming out of the black hole. These are the materials which are material and the radiation which is coming out of the accretion disk. Basically, when the material is falling through, some of the material gets escaped and it forms this jet. There will be one on one side of the accretion disk, one here and one in the below that we cannot see now. So these are the the jets that are again moving very fast. Some of them moving very close to the speed of light, and they are large in the size. We could see them in the telescope. I'll see one example that I can show you. They're very, very large in structure. So this is the typical structure of the black hole. There are variations of it, but this is the typical structure of the black hole that we can see. And we can see there is a event horizon again, which is right into this border of that black color black hole. And within that, there is a singularity. Now, if these black holes are invisible, how do we image them? How do we take a picture of them? And we took a picture of them recently that we can see right now. Okay. So this is the picture of the black hole that we can see on the right-hand side as it appears from the Earth. And this is the picture of M87 black hole, which is at the center of the M87 galaxy. And on the left-hand side, you see a jet, picture of the jet coming out of this black hole, which is taken by the Hubble telescope. And that's the center of the galaxy, which is brightly glowing. And this is the zone part of that black hole image. You can see that the black holes are named after their host with a star. So as you can see, there is this particular black hole is called as M87 star, which is the galaxy, which is the center of the M87 galaxy. That's a convention that we follow. We don't name them abruptly, but we name them as after the host that they are in. So this particular image, as you can see here, there's a center dark area, and surrounded by there's a glow area, which is the accretion disk. And the accretion disk, what we can see is there is a larger glow on the lower side than the upper side. It's because the accretion disk is tilted to an angle with our point of reference. So the material which is there closer to us is glowing brighter than the material which is farther than us. That's why we can see there is a bright side on one side and the little not so bright side on the other side. That's how we can see it here. So Event Horizon Telescope took this image, which is again a collaboration of various telescopes in various nations. And they have used multiple telescopes, multiple radio telescopes to image this. And we'll see now how it is done. And they have collected the data of all the telescopes together and then produced this image. Now this is the black hole image of the black hole which is present in the M87. Now let's look at the black hole image of our own Milky Way black hole. Okay, so this is again called as Sagittarius A star because this is there in the Sagittarius constellation at the center of our Milky Way. And again, you can see it is, if the image is similar, but we have a lot of bright spots here. Compared to the previous image, the accretion disk is little bit oriented towards us, towards Earth. So we can see more parts of the accretion disk, and that's how you can see a lot of glow around it. Not just once, but thrice, you can see the glow. And I'll be sharing a link where there's a deeper explanation about how do we understand this image, what exactly we are seeing it, what is the darker part, what is the lighter part, and then you will be able to see that how this image is taken and how what the image will tell us, and then you will be able to appreciate this. And as I said, the Event Horizon Telescope took this image by combining more than one telescope, which are spread across the globe. And all those telescopes were synchronized in time, and they were tuned to observe same black hole at the same time. And they collected the data over a period of time, and they took that data, flew all the data into a central place, and they combined the data. There were more than 100 hard disks of worth of data, the raw data collected by each of those telescopes, and they had to combine that with the software, and then they created this kind of an image. And literally, they had to flew those hard disks into this central place, and they found that the internet speed is not that adequate for them to transfer all the data to the central place. Okay, so this particular, the picture shows where all those telescopes were. As you can see, they're all spread across the entire globe. And this was needed because what we were observing was very small, very small. Even if you have, you remember I showed you one picture, which was the jet coming out of the black hole, which was taken by the Hubble telescope. Even though the Hubble telescope is in the space, has a good resolution, but it couldn't able to image it because the resolution has to be very, very huge. These black holes are very, very small. Hence, we had to get a resolution as big as the Earth itself. So all the image was taken from all these telescopes and then combined, a technique called as interferometry, and then entire data is merged to form a single image. Now, let's look at primordial black holes. This is the interesting type of the black hole. Although this was only theorized at this moment, we do not have the observational evidence yet. But this is connected to another mysterious thing called as dark matter. Dark matter is a thing, as you might know, is a mysterious thing that exists in the universe, which has the gravitational effect on the visible matter that we can see and feel, and due to which the galaxies are moving or rotating around themselves faster than needed or faster than we observe to be. And we believe that this dark matter is the one which is causing that. And while predicting primordial black holes, scientists also say that primordial black holes are good candidates for dark matter, explaining the dark matter. So again, these are the black holes which are born right after the Big Bang, right after the first few seconds of the Big Bang, and they come in all kinds of shapes and sizes. And there is a theory that these black holes could come in the form of in the sizes of a planet or an asteroid or a star, which creating the gravitational effect of the dark matter. So we don't know fully yet, but the prediction is that dark matter is the primordial black holes are the best candidates for explaining the dark matter. But again, there'll be a lot of research that's going on currently, and there are future missions, space missions planned to observe these primordial black holes directly. And there are various instruments which are being set up which are called as LIGO instruments, which helps us to detect the gravitational waves that we can identify if there is a large disturbance happens within the space-time due to a collision of large mass things like a black holes or a neutron star. Maybe we'll be able to detect it in the future. So with that, I think let's look at what are some of the recent interesting research happening around the world on the black holes. Now let's look at, let's start with the primordial black hole themselves. So these were again, as characterized to be a good candidate for explaining the dark matter, but there are a couple of papers which I would like to highlight here, which came last year in the September, and this one came in the January this year. So these two papers predict that the primordial black holes could be size of an asteroid or a small planet, which may be passing through the solar system. And if they do, we should be able to detect that by observing the tiny disturbances on a planet or the moon of a planet, because we have been observing the planet's trajectory, the orbits, and the moon trajectories around the planets for so long. So we have a good prediction about how these individual orbits behave. So if there is a primordial black hole, which is of this size of an asteroid or a small planet, which is passing through the solar system, it will disturb or object some of these orbits because of the gravity again. And if that happens, we should be able to detect it. And so basically, it's a cool idea where you use a solar system as a dark matter detector, which is a cool thing. In today's world, there are lots of dark matter detectors built usually well within the Earth's crust. I mean, the kind of like a gold mine or an abandoned mine, where they try to observe if there is a dark matter particle which is getting hit, and we could detect them by conventional means, like there is a light or there's not a light or something like that. But this particular idea is very cool because it proposes to observe use the solar system as a dark matter detector. This is very cool. Okay, so we'll see. Time will tell. So another cool discovery that happened sometime January this year again is a series of observation that happened in one of this particular galaxy, where scientists were able to observe the jet formation in real time, almost in real time. This particular galaxy has been observed in the observation for quite a long time, and we knew that there is a black hole at the center of this galaxy. But while observing this galaxy towards the end of last year, we could see that there's a sudden change in the brightness and the X-rays together at the same time from this galaxy. That indicates that there is some change happened, kind of like a change where a star might have wandered very close to this black hole, and the jet starts forming and jets starts emerging out of that. And this is the first direct observational evidence that we could see that how jets formed or just forms around the black hole when the material falls onto them. Okay, so yeah, there's another cool interesting thing that I would like to show you. This is again a recent discovery of again observational evidence. I mean, this is theorized to be kind of a thing where very weird where the black hole can form without the help of the stars. Black hole just form out of a dense matter. It doesn't have to be a dying star to form a black hole. So that was just a prediction. And this particular observation was confirmed, right? And this particular observation, the scientists used two telescopes, Chandra X-ray telescope and the JWST, James Webb Telescope, to observe the black hole of a galaxy at the same time. They found that the black hole wasn't existing earlier in this galaxy, but again, suddenly it formed and started emitting X-rays. And emitting X-rays usually are associated with black hole. So if that X-ray jet is coming towards you, it's directly oriented towards you. That thing is usually called as quasars. Otherwise, if it's emitting elsewhere, it is you could observe it, just as in the case of M87. We could see a large jets coming out of that. So this is the direct, again, observation evidence of a black hole. Again, a small black hole, stellar size black hole. It could form without the need of a star. Again, this is a very cool discovery. And yeah, again, there's a lot of research going on to this particular topic and the previous topics, especially the primordial black hole. There are many scientists doing observation and the research on it. And yeah, these are the three things that I wanted to highlight. What's the cool thing about black holes, which is happening in the recent times. And of course, there are lots of other research happening related to black hole, related to the dark matter together, which are quite interesting to see. But I found these are the quite cool things to look further. So I'll drop these links into the description. Now, coming to what's in the future for black hole research. Okay, so this is always an active research topic. Next to the dark matter itself, there are lots of teams in universities working around the globe to find out what it's all about, what it is black hole is made up of, how they behave, what they contain inside it, and all that. So I would like to highlight this one. One is our own ISRO XPOSat mission, which was launched in January. This is the satellite, which is a telescope which observes X-ray emissions. It is capable of observing X-rays from all various sources, but it can also observe X-ray emissions from the black hole and the supernova remnants. And recently there have been multiple papers on it, and there's one paper that I would like to highlight that they were able to point this telescope to a supernova remnant, which is in the Cassiopeia, and they were able to observe that the emitted X-rays, the light had the signatures of the materials, the minerals like iron or nitrogen, oxygen, and kind. So it's a cool thing that this telescope could detect those materials just out of the emissions which are coming out of that supernova remnant. And the other interesting space probe that's going to launch a little later, like 2030, is Laser Interferometer Space Antenna, which is also called LISA. This particular one, which is being built by European agency, Space Agency, ESA, and this space probe is actually three of them will launch together. They will form LIGO, laser interferometry observation in the space, just as we have on the Earth. They'll form that interferometry telescope where they can observe the disturbances or the uh, frequencies within coming within the space time itself, that gets generated when two massive objects collide, and they can observe the gravitational waves. And why space? Because this is again, there's no other disturbances that you could get. You could silently observe, silently listen to it. It's just a matter of you know pointing them in the right direction at the right time so that we can observe those gravitational waves coming towards Earth. Um, and another one which is very specific to the black hole, which is Advanced Telescope for High Entry in Astrophysics, which is called Athena. So this one is again an X-ray observatory, which is going to launch in 2030, very specific to observe the hot energetic objects, including black holes. So this is very tuned to frequencies of X-rays where there is a lot of emissions that happen, known to happen out of the supermassive black holes. There's another one which is called as Black Hole Explorer. This is again a space probe, which is going to extend the Event Horizon Telescope and uh, um, aim to capture the images of the photon sphere, the sphere, the right next to the black hole surface. This is going to launch early 2021, and this will also form as another telescope when EH2 takes a future images of a black hole, but this operates from the space. Einstein probe, going to be it's already launched by the Chinese Space Agency. Again, this is X-ray scope, space telescope observing X-ray emissions. There are lots of papers which are being published from the data produced by this telescope already. Looks very interesting because this is very much tuned to that particular spectrum of the X-ray where we can see the X-ray jet coming out of the supermassive black holes. Okay, so these are some of the black hole research that are upcoming or which is already like in the works. Now let's switch to one of the video that I would like to show you and see how that functions. Vishwa, maybe you may need to help me out here. I'll start the video, see if it functions fine. Let me know. So this is the video that was produced by Event Horizon Telescope. This is actually the journey from the outside of the M87 galaxy into the M87 black hole. So it's very interesting how this journey happens. It's again a combination of various images and observations, and again computer simulation built into it. So let's see how that works.
Yes, the simulation works fine. Let's see the video.
Okay, great. Thanks. Okay, so as you saw, we went from the Earth towards the M87 black hole, M87 galaxy, and peered into the galaxy itself to reveal the black hole. Okay, so this is another video which will do that similar thing with our own Milky Way black hole. Let's see. Okay, so that was clear and visible. So this is the session that I wanted to do today. Again, as you can see, we just visited black holes. What are black holes? Basically, they are the places where strong gravity exists, so that it doesn't allow anything, even the light, to escape. We saw what are the types of black hole, including the one which is predicted, called as primordial black hole. And we saw the structure of the black hole, which consists of the event horizon and the singularity and the accretion disk and the jets moving around. And we also saw what are the discoveries that happened around the black holes. The first image of the black hole, the second image of the black hole of our Milky Way galaxy, and some of the recent uh, research and the observational evidence of theories that we saw. So I hope this was kind of like a glimpse that I trying to give to you with respect to the black holes. And again, it hope this increase your interest to study more of the black holes and get amazed by that mysterious places in the universe. And yeah, I'll be um, sharing some of the links, including the videos that I played at the end, in that YouTube video description and the comment, so that you can refer them. I would also be sharing the links to those research papers which I highlighted, so you can look at them and then find out more about that. And yes, let me know if you have any questions. And yeah, thanks for your time.
Vadraj, I have a few questions on our WhatsApp channel. First of all,
Yeah,
I had a personal question. So you showed this picture
sure.
about LIGO, different locations of LIGO locations, some in US, some in Europe, South America, Antarctica, all over the world, with a reasonable amount of angular separation when it comes to when it comes to us on Earth. Now,
Hmm.
M87 itself is at least a few million light years away.
Hmm.
Now, how how does all these locations of LIGO with just a few degrees of, probably less than a few degrees of separation with respect to M87? If I mean,
Hmm.
hypothetically speaking, if you're standing somewhere close to M87 and
Hmm.
looking at Earth, Earth is but a small speck.
Hmm.
uh, a few minutes in angular width or
Hmm.
seconds probably.
Hmm.
These different locations, how do they really help? I mean, would it have been better? Would we have had better resolution if we had one LIGO observatory here on Earth and another one on Mars, another one on Jupiter? Would that have helped?
Yes, definitely. So these event horizon telescopes, which are located in these different parts of the Earth, were chosen to see that the first thing that they were chosen because they were quite capable of observing on that observation period. That's the first thing, and they're all radio telescopes.
Mhm.
The second thing that happened was this M87 was chosen to be a first target of black hole imaging because that happens to be at the right place, at the right distance, having a right size. I mean, right size when we observe from the Earth. Although the M87 galaxy itself is quite far, more than 55 light years from the Earth, it's huge. Even this M87 galaxy black hole itself is huge. More than the size of our solar system. But it happened so that because of the distance, because of the size, it fell right within that resolution of this all telescopes combined together. That's how we were able to see that we're using this kind of a telescope arrangement. we are able to image that M87 black hole to not to that accuracy. We could see that there's a lot of blub area, but yes, we could
Yes.
increase the resolution, by using other techniques and so on and so forth. But the first image that came out was very blurry, but we were able to see that, okay, this is accretion disk, this is the shadow of the black hole, this is which is what's surrounding it. That's how we were able to make out. And the two reasons that, to answer your question, the two reasons that these telescopes are chosen to be there is because of those capabilities and the capabilities themselves, that they're radio telescope and they were able to observe it, and they are at this kind of a distance. As you can see here, there are lots of redundancies built into it. You can see there is a lot of telescopes right within the Europe itself.
Yes.
Okay, and there is some telescopes which are spread across the United States.
Yes.
Okay, so those redundancies would all help a little bit to fine tune the data and then get a clear picture. But if you see the image of the black hole which is produced for the first time, as you can see here, which is totally blurred. And the recent images of the EHT, which were much more clear than this one, the first telescope that the first image that produced, because they had a lot of other techniques. They used artificial intelligence to clean up certain parts of it, but still they were able to achieve the feat of this kind, which was never attempted earlier. And the way they have arranged is, first of all, if you have large number of telescopes working across different time zones, synchronizing them is a big difficult task. Yes. That they were able to achieve it. And once they do the synchronization, having them observe the same target at the same time is again a challenge, because Earth rotates, keep rotating around the sun, so you have to really point them in the right direction and the right angle so that they're able to capture that data, observable data, and then again transferring all the collected data and then into a central location and then combining them with a lot of algorithms, which was again a challenge. But yes, they were able to do it, and then now we know how to image a black hole. That's it. But yeah, thanks for that question.
Thank you very much. A follow-up question. There is this M87. In M87, why is light seen only on the underside? Yeah.
You mean this one?
Yes.
Yeah. So I briefly explained, because this is again, this brighter part is the light coming from the accretion disk, and the accretion disk is at an angle from our point of view. Okay, just not at the edge on, which is not on the flat on, but it's on the angle. So what happens is the matter which is coming, so the matter is rotating around the black hole, and the matter which is coming towards us becomes brighter, and the matter which is going away towards it becomes little fainter. Not that faint, but yes, it is fainter than compared to this brighter one, because this is again due to the Doppler effect. The things which are coming closer to you will have a brighter frequency than the one which is moving away. It is same as the Doppler effect that we see in sound. So the light also behaves the same way and with the same phenomena. So that's why you can see the large bright spots in this image, only concentrate on the center, but not on the other side. But when you compare this image with the image of the Milky Way black hole, it looks totally different, as you can see here. So all due to the orientation of the accretion disk with our point of view.
Okay.
Hope that helps.
Yes. Another question that's been asked is there a threshold for a black hole to form? As in, say, is there a mass threshold? Is there an energy threshold below which a black hole does not form, or above which we are sure that it's a candidate black hole?
Yeah. So I explained a little bit about that over here. There was something called a Chandrasekhar limit, which is 1.4 times mass of the sun,
Mhm.
which is what is the resulting factor. If everything which is having less mass than this limit, which we see that that star will not end up forming a black hole. But if that mass of the star, that mass of the dying star, is between this range, like the 2.5 to 3 times the mass of the sun, then there is a high chance that it will end up in black hole. Because what happens here is there will be a high mass concentration in a less space, very dense space. So eventually, all the material, all the matter which is there in the star will get collapsed due to its own gravity, and eventually the gravity will become so strong that everything will just rift into a single location, and hence it will turn out to be a black hole.
Okay. Couple more questions.
Yeah.
How common are black holes? Whether they're small or big, how common are they in the universe? Does every galaxy have a black hole?
Does every galaxy has a black hole? Yes, that's how we have been observed too. Every galaxy has a supermassive black hole at the center of it, especially the one which are the whirlpool kind of galaxies. But there are other galaxies which are just there across the universe. Some of which we don't know because they're all, get merged into space blackness. But they get emitted, they get starts emitting light, and then we were able to detect them by just by chance or by just looking at them. So one of that is an example over here. So in this case, there was a galaxy, and there was the prediction that in every galaxy has a black hole. So is this galaxy as well, but we didn't know that there was a supermassive black hole over here, and that black hole did not have its own jet, and it suddenly started producing a jet. So yes, there are many types of black holes, and all these three black holes known to exist. And this is the one which is predicted, which is not observed. But some of these stellar black holes, intermediate and supermassive black holes, have been observed indirectly. Again, by using the mass which is falling onto it, and that gets heated up, and that start glowing, and then you can see the black holes, and then all the accretion disk material starts revolving around the black hole. By using the speed of that, we were able to predict how big is black hole, how massive is that black hole, and that's how we are able to categorize them into these multiple types of black holes. Yes. Hope that answers your question.
Yes, yes. And I have this one final question, I think. Well, why is it that we see the X-rays only from black holes? Why is only X-rays being emitted from black hole? Is that right? Is it just X-rays, or is it uh, there are other uh, electromagnetic radiations
Yeah,
as
that's
well
a that's a
that,
question.
that the
Yes.
black hole has?
So what we see is in those jets, mostly the X-rays coming out of it, because X-rays are known to have high energy. There are gamma rays as well, which are known to come out, but it's mostly X-rays, and some part of it is visible. There's a huge jet coming out of M87. But why X-rays? Because X-rays are known to be associated with black hole jets. That's kind of like observed in multiple cases related to the supermassive black hole or the intermediate black hole. So that's how we can say that mostly the radiation just coming out of that consists of X-rays, but some of that is visible and some of that is gamma rays.
Okay. I think that's about all the questions we have.
Cool.
Let me also, just a second.
Sure.
Yes, that's about all the questions we have. So thank you very much,
Cool.
Vadraj. Really
Okay.
appreciate
Thank you.
you taking out time talking about a topic that is of interest to everybody, and especially in our start parties, there are at least a few people who ask, is it possible to see a black hole? How big are black holes? And if
Yeah.
somebody falls into a black hole, what happens? All kinds of questions.
Hmm.
Uh, so thank
True.
you very much for throwing some uh, light on a black hole. Uh,
Yep.
Really appreciate your time. Thank you very
Cool.
much.
Okay. Thank you. Thank you so much.
Thanks. Bye bye.
Bye.